Okay, welcome everybody to our first N3AS seminar of the fall semester. And today we're very pleased to have Amol Patwardhan from SLAC, who will tell us about NuP process nucleosynthesis in core collapse supernovae. So please, Amol.
All right, so thank you, Evan. Thank you, Lukash, for inviting me to kick off the seminar series in the fall semester or quarter, depending on your affiliation. So my talk today is going to be about some of the work that we have been doing at SLAC over the past year and a little bit more with Alex Friedland, his former graduate student Payal, who will now be a neutrino theory network postdoc at Berkeley, and Shuo, who was a rotation student with him sometime last year. So this is about NuP process nucleosynthesis in core collapse supernovae, which is a particular type of proton-rich nucleosynthesis. And we will specifically look at the impact of neutrino-driven outflows and flavor mixing between neutrinos on this NuP process. So, okay, so all right, so for the first half of my talk, I'll be setting the stage, just giving an introduction and an overview. And in the second half of the talk, I'll be talking about our specific work. And so in the first half of the talk, I'll start by talking a little bit about core collapse supernovae, the role of neutrinos and their flavor oscillations. And then I will switch gears and talk about the origin of proton-rich elements in nature and give an introduction to the NuP process. And then we will come to the second half of the talk where I'll discuss the details of the effects of hydrodynamics and neutrino mixing. Okay, so as we know, core collapse supernovae are the final stage in the life cycle of massive stars, which are heavier than about 8 times the mass of the sun. And these stars undergo core collapse when the iron core, or in some cases, the oxygen neon magnesium core mass exceeds the Chandrasekhar limit. It's about 1.4 times the mass of the sun. And this corresponds to when the gravity overcomes the pressure support that can be provided by electron degeneracy, which is that you cannot cram too many electrons into a small volume. And so when the core becomes too big, there isn't really anything that can stop, or there isn't anything that can hold it up. So it just implodes. And it just keeps collapsing all the way until it reaches nuclear density. Now, at that point, it cannot collapse any further. And so the inner parts of the core just like hit a hard stop. But then the outer parts of the core are still infalling supersonically, and they are causally disconnected from the inner layers of the core. And so this causal disconnect sends a shock wave ripping out through the outer layers of the core. Now, as this shock wave expands, it loses energy. And this mainly happens because the shock wave photodissociates heavier nuclei into essentially free nucleons and alpha particles as it passes through the outer layers of the star. And in numerical simulations, it was observed that the shock wave basically stops. It loses all of its energy and it becomes a standing shock wave before it can completely blow up the star. But now, on the contrary, we know that core collapse supernovae exist in nature. I mean, we see them all the time. Like in a given galaxy, they are not that frequent. You have them about once or twice per century, but because they are so bright, we can see them like even when they are in galaxies very far away. And so on the scale of the universe, they actually happen quite frequently. And so then we have to explain like how the heck they happen. And so there has to be something that revives the stalled shockwave by putting enough energy into it. Now, we don't know the details of this, but we do strongly suspect that neutrinos have to play a major part in this. And this is because we know that core collapse supernovae are neutrino factories. Neutrinos happen to be the main carriers of gravitational binding energy and lepton number, which is radiated away from the star through this process of core collapse. And if you just do a back of the envelope calculation, the gravitational binding energy that is lost by the star during this core collapse phase is about 10 to the 53 ergs, which is a substantial fraction of its rest mass of order 10%. And that amounts to about 10 to the 58 neutrinos with an average energy of 10 MeV, being emitted over a duration which is of order 10 seconds. So that's an enormous number of neutrinos and a lot of energy. And so if you can make even a small number of those neutrinos interact and transfer their energy and lepton number, they can cause havoc. I mean, in particular, if say you can get about 1% of the energy out of the neutrino field and transfer it behind the shock, then that can be enough to revive the shock and explode the star. Also, even in the aftermath of the explosion, this continued neutrino-driven heating can drive significant baryonic matter outflows from the surface of the nascent neutron star. And this energy deposition is mainly driven by charge current captures of electron flavor neutrinos and antineutrinos on protons and neutrons. Now, there is a reason why I said electron flavor, and that is because the typical energies of these neutrinos are of order tens of MeVs, few tens of MeVs. And that is not enough to make muons or tau leptons in the final state. So only electron flavor neutrinos can participate in these charge current reactions. And so that makes them flavor asymmetric, but that also means that you really need to understand the flavor evolution of the neutrinos really well to know what's going on. So let's briefly look at the various stages of neutrino emission from core collapse supernovae. So neutrino emission becomes already significant during the later stages of neutrino burning, from carbon oxygen burning onwards. So this is before core bounce. Then you have the early stages of core collapse, where electrons are being captured on protons, and so the core is being neutronized. And in the process, you release a lot of electron flavor neutrinos. And in the early stages of this, the density of the core is not high enough to actually trap the neutrinos. And so neutrinos being produced in this stage are just free streaming out pretty much. But then eventually the core becomes dense enough, and then you have core collapse and core bounce. And at that point, the core is dense enough that it traps neutrinos behind the shock wave. But then eventually the shock wave moves out into regions where the densities are again sufficiently low for the neutrinos to escape. And this gives you a neutronization burst, which is this peak of the neutrino luminosity, which can be a few times 10 to the 53 ergs per second. And this peak is because these neutrinos are produced by neutronization, it's mostly electron flavor neutrinos, and this happens at a time of about 10 milliseconds after core bounce. Then after that, the shock wave stalls, and there you can also have an accretion phase where matter is falling in through the shock wave and accreting onto the surface of the nascent neutron star. This happens over, say, a few hundreds of milliseconds. And then, of course, after the explosion, you have the late time phase where the protoneutron star cools and contracts over, say, a few seconds to 10 seconds by emission of thermal neutrinos of all flavors. And so these are the different phases of neutrino emission. And during many of these stages, as I mentioned, the neutrino luminosities can be quite substantial. And so in many of these phases, the energy and lepton number transport becomes obscured by collective phenomena in neutrino flavor oscillations. And these collective phenomena are driven by interactions of neutrinos amongst themselves. So neutrino-neutrino interactions. Now, this is like an example of a flavor evolution equation in the coherent limit, where you are neglecting neutrino-neutrino collisions. This is only in the forward scattering regime. And you are also neglecting neutrino-neutrino correlation. So this is like a one particle effective evolution equation. But even with those simplifications, you can see that there are two substantial complications in this. So the first complication is non-linearity. So in this neutrino-neutrino part of the Hamiltonian, you can see that the Hamiltonian depends on the density matrices of the neutrinos. And so basically the flavor evolution of the neutrinos is driven by a Hamiltonian which itself depends on the flavor. And so that's the nonlinear feature of this. And then the other feature of this is the geometric complexity, where you see this dependence on the intersection angle between the neutrino trajectories. And so both of those effects can make this thing quite complicated. To simplify things, you can impose some symmetries like spherical symmetry or azimuthal axial symmetry. And this has been done in the last couple of decades. And by doing these calculations, people have seen various kinds of interesting collective effects like synchronized oscillations or bipolar oscillations. And these effects are observed in different regimes, like where the let's say the neutrino density is comparable to the matter density, or the neutrino density is comparable to the vacuum, mixing term, and so on. And so you can see roughly illustration of the different regimes. So initially you get the synchronized regime or neutrino enhanced MSW. Then you have the bipolar regime where you get large amplitude oscillations of neutrino pairs. And then you have the regime where basically the neutrino densities become insignificant as you move far enough out in radius. And so there you only have ordinary MSW or vacuum like oscillations. As a result of the interplay of all of these regimes, you end up with these interesting neutrino spectral features called spectral splits or swaps, where neutrinos at a certain energy, where neutrinos above or below a certain energy can completely change their flavor, whereas the neutrinos on the other side of the split more or less remain in their initial flavor. So this is, if you impose certain symmetries like spherical symmetry or angular symmetries essentially. But recently, of course, there has also been a lot of interest in exploring regimes where you relax some of these symmetries and where you allow non-trivial angular distributions of different neutrino flavors. In particular, if you have electron-lepton number crossings in the angular distributions, then you can get significant flavor conversion on much shorter time scales than bipolar oscillations, within say a few kilometers or a few tens of kilometers from the neutron star, as opposed to hundreds of kilometers. And this can have even more interesting implications for shock reheating and nucleosynthesis. If you're interested, you can check out these recent reviews by Irene Tambora and Shashank Shalgar, and also by Sherwood Rickers and Manivrata Sen, former N3AS postdocs. So even other than what I've mentioned so far, there are other very interesting problems in collective neutrino oscillations. So there are collisionally triggered collective flavor instabilities, which Luke Johns has extensively worked on. Then there is the halo effect, which can come from neutrinos which undergo direction changing scattering and sort of come back in. And so here you have flavor information propagating in all kinds of directions rather than just outwards from a neutron star surface. And then, of course, you have these effects where you try to consider the fact that neutrino oscillations driven by coherent neutrino-neutrino interactions actually represent a quantum many-body problem. And you can have non-trivial quantum correlations or entanglement between neutrinos. So here I can take the opportunity to shamelessly advertise my own work, but then also the work of some others and groups, some of which are affiliated with N3AS, like Amol or Zeve. And this is also interesting because this sort of brings in connections to quantum information and quantum computing. So this is all I have to say about neutrino flavor oscillations. At least maybe towards the end of the talk, I can come back to it a little bit. I will now switch gears and talk a little bit about the origin of proton-rich elements. So here you can see a chart of all the nuclides. So this is the nuclear physicist's periodic table. You can try to zoom in on a particular subregion of this, and you see that the stable nuclei in this chart come in basically three branches. So there is this central river along which most of the stable nuclei are located. But then there are some outliers over here which represent the more neutron-rich stable nuclides. And then there are outliers over here which represent the proton-rich stable nuclides. So most of the nuclei along this central region are made in what is called the S process, or slow neutron capture, whereas the ones on the right have to be made by what's called the R process, or rapid neutron capture. Now that's something that is interesting in and of itself, but that won't be the subject of my talk. What I'm instead interested in are these nuclei on the left side, or on the more proton-rich side of the valley. And so we will try to talk about the origin of those. So this is, another way to look at this. What you can see here are the naturally occurring abundances as a function of mass number for various branches of these nuclei that you saw on the previous slide. So on the top, you can see the two curves here, which correspond to the S process nuclei and the R process nuclei. And on the bottom, this curve is what represents the proton-rich or P nuclei. Now you can see that, throughout most of this range, the P nucleide abundances are about a couple of orders of magnitude lower than the S or R process nuclei consistently. But then there is this peculiar region in between mass number 90 and 100, where the P nucleides get rather close in abundance to the S or R process nucleides. So this suggests that whatever process makes these other P nucleides may not be the same as the process that makes these ones, like just because the pattern looks different here. And the nucleides that are of interest within this region are 92, 94 molybdenum and 96, 98 ruthenium. So most of these other P nucleides can be made by making the neutron-rich nucleides first and then transmuting them in some way, for instance, via photodisintegration. So you irradiate neutron-rich nucleides with gamma rays and then you kick off some neutrons, and that leaves you with more proton-rich nucleides. So this is called the gamma process. Then there is the new process where you can like directly transmute neutron-rich nucleides into proton-rich nucleides by neutrino capture. But then those processes have some difficulties. If you have to explain the abundances of 92, 94 molybdenum and 96, 98 ruthenium, and it's you really need you either cannot do it or you need really fine-tuned designer conditions to get suitable amounts of molybdenum and ruthenium. And so then that begs the question that if you can't make these easily by transmuting neutron-rich nucleides, then could you try to make it directly by capturing protons? Now that is a bit difficult to do because proton captures are harder to do than neutron captures because they have Coulomb barriers. So you need a few conditions for this to work. First of all, you need a lot of free protons. You need some seed nuclei like nickel 56. And you need temperatures that are high enough to overcome these Coulomb barriers, but not so high that the forward and reverse processes are in equilibrium so that you can never grow, beyond IN56. And so that picks out this range of temperatures between 1.5 gigakelvin and 3 gigakelvin. And within this range, the temperatures are such that you can actually grow from nickel 56, to higher mass numbers depending on the exact environment. Now, this suggests that matter outflows from core collapse supernovae could be candidate sites because there you have matter that expands and cools from high temperature and density. Now, there was this process called the classic RP process, where you had a sequence of rapid proton captures interspersed by beta plus decays. But then that runs into a problem that some of these beta plus decays have really long lifetimes. So these are called waiting point nuclei, like germanium 64. And so the lifetimes of these nuclei can be as long as a few minutes or a few hours, whereas the dynamical timescales can be seconds or shorter. And so if you invoke the RP process, it basically stops at germanium 64. And so you need something else. Excuse me. So then a new mechanism was proposed around 2005 to get around this difficulty. And that was based on recognizing that these outflows of matter expanding from high temperature and density near a core collapse supernova are also accompanied by tremendous fluxes of neutrinos and antineutrinos. And so this mechanism was called the NUP process, proposed initially by Karl Fröhlich and collaborators. And this was basically based on the idea that in a proton-rich, outflow expanding from high temperature and density, you can have electron flavor antineutrinos capture on protons, and it gives you a subdominant neutron population. You can convert about a few percent of the protons into neutrons, but that can be enough to trigger either NP exchange reactions or neutron capture reactions, which allow you to bypass the beta plus waiting point nuclei like germanium 64. And if you can make this happen in the right temperature range, then you can actually grow your nuclei far beyond these waiting point nuclei. Of course, at some point this process ends. Once you go below 1.5 gigakelvin, you hit Coulomb barriers and you can't grow these nuclei any further. So this, just the basic understanding of this physics allows us to list what physical conditions are favorable for this NUP process. So basically what you need for this NUP process to happen is a high proton to seed ratio at 3 gigakelvin, which is when the NUP process can efficiently begin. And you need a high integrated electron antineutrino fluence because that is what determines how many protons you convert into neutrons. Because as we saw earlier, we need both protons and neutrons, right? So you need the neutrons to bypass the, the beta plus decay waiting points. And so the conditions which facilitate a high proton to seed ratio are a short time interval for T greater than 3 gigakelvin. Because if that time interval is too long, then you basically make too many seed nuclei, and then you don't have a high enough proton to seed ratio. You need a high entropy per baryon in the outflow, because that also is conducive to having lots of free nucleons per seed. You need a high proton fraction, because ultimately, if you want to make proton-rich nucleides, you'd better have free protons. And you need a long time interval in the 3 gigakelvin to 1.5 gigakelvin band, because that is when you are, essentially growing the plume, right? And that's how you get like that's how you get a higher nu bar fluence within that band, just by giving it more time. And so there are some of these other papers which discuss these criteria. So this sounds very promising and elegant, but then since it was originally proposed, several papers raised a number of questions about whether this can actually work in a realistic setting. So there were some papers which questioned whether you can make molybdenum and ruthenium in the correct ratios, or whether you can even make enough of them to explain the solar system naturally occurring abundances. In particular, these issues became particularly dire with a recent paper that was published in Nature a couple of years ago. And the argument of this paper was that if you take into account in medium enhancements of the triple alpha reaction rate, which is basically triple alpha going to carbon 12, then that leads to an increase in the seed nuclei formation. And so it reduces the proton to seed ratio in the outflow, and it substantially decreases the nuclear process efficiency. And so this seemed to be a nail in the coffin of the NUP process. Like they seem to, so it was already, the NUP process already seemed to be in difficulty before this work came out, and then this even made it worse. And so it seemed like the NUP process was essentially unviable to make enough molybdenum and ruthenium. And so this got a lot of attention. There was a press release, and the general picture seemed to be that we need to come up with another way to make molybdenum and ruthenium. But then my collaborators Alex and Payal, they were working on a different project which had to do with neutrino-driven outflows and their signatures in Dune. And so Payal had a very nice spherically symmetric hydrodynamic code through which he could self-consistently generate these outflow profiles. And so we decided to use these outflow profiles to re-examine the nucleosynthesis problem. And so one feature of what she had discovered from running her outflow profile code was that neutrino driven outflows can be either subsonically expanding or supersonically expanding, depending on the exact boundary conditions that you impose on the outflow equations. And so you can basically, as you see here, you get different families of solutions. So the figure on the top here is like a phase space plot, so velocity versus distance. And so you have some regions of phase space where the outflow expands subsonically, and some regions where the outflow expands supersonically, and they are separated by this critical solution. You can look at the same solutions in terms of the density profiles. And in this region up here, you can see the smooth subsonic profiles, whereas here you see supersonic profiles which are terminated by these wind termination shocks. So the way this is done is you solve three relatively simple looking outflow equations. So this is mass conservation, this is momentum conservation, and this is energy balance. And then you can add more corrections to this from general relativity and so on. You can change these variables into different sets of variables like temperature, entropy, velocity, pressure, and you can impose boundary conditions at the near boundary or the far boundary, and then you can obtain families of solutions this way. So what we discovered by doing so is that if we take these different kinds of outflows and we couple them to a nucleosynthesis network, then we discovered that subsonically expanding outflows can actually do much better in terms of obtaining good NUP process yields than supersonic outflows. And there are two reasons for this. One reason is that the outflow spends more time in the 3 gigakelvin to 1.5 gigakelvin temperature band. And then the second reason is that if you have an outflow that is expanding subsonically or slowly, it spends more time closer to the protoneutron star where the neutrino fluxes or the nu bar fluxes in particular are higher. And so you can convert more protons into neutrons. And as we saw earlier, that a higher nu bar fluence actually increases the chances of a better NUP process. And so if you take all this into account and you take the in medium triple alpha enhancement into account, yes, it does weaken the NUP process a little bit, but not to the extent that it can just kill it completely. In addition, as I discussed earlier, you do also need a high entropy because a high entropy facilitates a higher ratio of free nucleons to seeds. And if you try to self-consistently obtain outflow solutions from the hydrodynamic equations, then a high entropy corresponds to having either a heavy protoneutron star or a relatively compact protoneutron star. But these numbers are not crazy. I mean, especially if you look at sophisticated 3D simulations of supernova explosions, especially for heavier progenitors, say heavier than about 12 solar masses, then 1.8 solar mass protoneutron stars emerge naturally from those simulations as a result of an extended accretion stage. And so here we present a comparison between NUP process calculations for a subsonic outflow and a supersonic outflow. So the supersonic outflow used here is one we adopted directly from the 2020 Nature paper. It had an entropy of 80. And so we tried to make a subsonic outflow which had a similar entropy. And so we used these protoneutron star mass and radius parameters. And you can see here in this inset that you have these different outflows here. So the green is the supersonic outflow with the termination shock, and the purple is the subsonic outflow, which you can see spends much more time in this yellow temperature band. And if you run a nucleosynthesis network with this, what we observed was that the subsonic outflow makes almost a couple of orders of magnitude more molybdenum and ruthenium compared to the supersonic outflow. And so this is good news because you can basically, in some sense, counter the effect of the triple alpha suppression by just letting the outflow spend more time in this yellow temperature band. So the way we do this nucleosynthesis is by using the open source Skynet nuclear reaction network, and we implement the triple alpha enhancement using the same prescription as the authors of the Nature paper. We take a time varying neutrino luminosity, which decays exponentially with a time constant of 3 seconds, which is reasonable. And to impose the boundary conditions on our outflow equations, we use post-shock densities from simulations by Sugbold et al. So this is what a typical calculation in Skynet looks like. You can make movies out of it, and you can see here a nuclear plume growing on the proton-rich side of the valley. So we can do this for different progenitors. And what we generically observe is that for heavy progenitors, subsonic outflows are more likely. So here we have examples with 13 solar mass progenitor on the left and 18 solar mass on the right. And you can see that in all cases, you have certain snapshots of time. So what we do is, because our neutrino luminosity is time varying, we can construct time varying steady state snapshots of outflow profiles. And you can see that generically within the first couple of seconds after core bounds, the NUP process yields can be quite good across a range of progenitor masses. And so you don't need a lot of progenitor fine-tuning to get these results. What you can do is you can also calculate the integrated yields across all these different outflow profile snapshots. I won't go into the details of this in the interest of time. But then you can get the integrated yields and you can compare those yields. You can compare the yields of different nuclides to each other, and you can also compare them to the threshold that you need in order to account for the solar system abundances. And from both points of view, we observe that we can actually, we can meet both of those criteria. All of the abundances of these different nuclides can be within a factor of 10 of each other, which is generically accepted as the requirement to produce them in the correct ratios. And they are also above a production factor of 10 to the 5, which is the threshold that you typically need to explain the solar abundances. The production factor I have defined on the previous slide, but we can get back to it during the Q&A if you would like to know more. To contrast with a subsonic outflow, we also did a supersonic outflow calculation, which you can generically observe if you have lower mass progenitors, below 10 solar masses. So this is a 9.5 solar mass progenitor calculation, and you can see that the yields here are much worse. And again, that is also reflected here in these integrated yields. We investigated the variability in the yields by changing the protoneutron star mass as well as the protoneutron star radius. And by doing so, we are effectively changing the entropy of the outflow. That also ties into like the equation of state of hot nuclear matter, because mass and radius are related to the equation of state. Now, in the last part of my talk, I will talk very quickly about the effect of neutrino mixing. So these are like the results that we got relatively recently. So basically, let me describe what happens when you introduce neutrino mixing, right? So the nuclear composition of a proton-rich outflow at 3 gigakelvin, which is around the onset of the NUPI process. So there you have protons, you have alphas, and you have seed nuclei. You don't have that many neutrons because all of them have been already absorbed into alpha particles and heavier nuclei. And the relative abundances of protons, alphas, and seeds, they depend, like one of the factors that determines that relative abundance is the proton fraction prior to freeze out from nucleostatistical equilibrium, which happens around 6 gigakelvin. Now the electron fraction or the neutron to proton ratio at 6 gigakelvin is set by a competition between electron neutrino and electron antineutrino capture rates. Typically, in order to get proton-rich conditions, you need a slightly higher electron neutrino luminosity compared to electron antineutrino luminosity. But I mean, that's okay. You get that in some simulations. Like that's not unrealistic. Moreover, if you have any mechanism which can mix, let's say, NUI flavors with mu or tau flavors, then that can further enhance the proton richness of the outflow because it increases the NUI average energies. And by increasing the average energies, you increase the capture rates, and then you shift the equilibrium between neutrons and protons towards the more proton-rich side. So one thing that can do this is if we implement instantaneous flavor equilibration between the flavors. Something like this was done in a paper by Young and Jeve in 2020. And so we do this in order to avoid the complexities of flavor transformations, but nevertheless you get some kind of a proof of concept explanation as to what flavor transformations or flavor mixing can do. So we let the neutrinos propagate to a certain radius, and at that radius we just instantaneously mix all three flavors. Now we can change this radius of mixing and we can examine these different regimes. Like what if the neutrinos mix before NSE freeze out? What if the neutrinos mix between NSE freeze out and the onset of the NUPI process, which is also known as quasi-equilibrium freeze out? And what if the neutrinos mix during the NUPI process temperature range? And so, by making the neutrinos mix in these different regimes, you can observe different kinds of effects. One thing to note is that typically in the neutrino spectra that you get from core collapse supernovae, the hierarchy between NUI and mu or tau average energies is much more prominent than the hierarchy between NUI bar and their corresponding mu and tau antineutrino flavors. And so if you do any kind of flavor mixing or flavor equilibration, you can have much more of an impact on the NUI average energies as opposed to the NUI bar average energies. And so we can do this calculation using the same tools that we had used for the earlier part of this talk, Skynet and outflows. And what we observe is that flavor equilibration can actually universally improve the NUPI process efficacy. And so in this figure here, what you see is the effect of changing the radius at which flavor equilibration happens. So the yellow curve is where there is no mixing at all. So I call it R mix infinity. And so here you see that you don't have that much molybdenum and ruthenium. It's between an abundance of 10 to the -6 or to -7, which is kind of marginally insufficient to explain the solar system abundances. But then if you incorporate mixing on top of that, you get almost an order of magnitude improvement depending on where you mix. And in fact, the earlier you mix, the more of an impact you can have, which is not surprising. Particularly in the three different regimes that I stated a couple of slides ago. So basically, if you mix them early enough that you mix them before NSE freeze out, then you can just directly change the electron fraction. You can change the proton to neutron ratio, and that just gives you a higher proton to seed ratio at the onset of the NUP process. So this is dependent on changing the average energy of electron flavor neutrinos. Now, in the following two regimes, the electron neutrinos lose their importance because you basically don't have any neutrons left behind. By this point, all the neutrons are absorbed into alpha particles or heavier seeds. So there are no free neutrons. So increasing the NUE average energies does not do much in these lower temperature regimes. Instead, what you can do is you can increase the NUE bar average energies, and thereby you can convert more of the free protons into neutrons, which is also helpful for the NUP process. So this also gives you a slight enhancement, but not as much as what you would get by making the mixing happen before NSE freeze out. And so that's essentially the effect of neutrino mixing that we observe across these different regimes. So this leads me to the conclusion of my talk. I'm sorry for going a few minutes over time. The conclusion, I guess, is that NUP process appears to be alive and well, at least for now. Or another way to say that is that it's too soon to declare that the NUP process is dead. What we observed is that the hydrodynamics of the neutrino-driven outflow can be extremely crucial in determining the outcomes of the NUP process. In particular, subsonic profiles with self-consistently modeled outflows can do quite well, even if you incorporate the enhanced triple alpha reaction rates. And you can also get a little bit of boost from having the neutrinos mix their flavors close to the protoneutron star surface. As far as future outlook, what we would like to do is that we observe this variability of yields across simulations with different protoneutron star masses. And so this you can think of something that you can convolve with like an initial mass function of progenitors, and you can calculate how you can get different kinds of nucleosynthetic yields over a galaxy, and then you can incorporate galactic mixing timescales and do some kind of chemical evolution calculation. As I also mentioned, the dependence on protoneutron star radius suggests that there is also a handle on the nuclear equation of state. So let's say if you fix a particular protoneutron star mass, then you know that you can get different amounts of NUP process as you change the radius. And so there is this equation of state dependence on the NUP process yields. As we demonstrated in the last few slides, incorporating neutrino flavor mixing close to the protoneutron star surface can also change the outcomes. And this motivates coupling the results of these fast flavor neutrino transformations with a nucleosynthesis network. And ultimately, all of this was a spherically symmetric 1D model. And we would also like to test this using actual trajectories that you obtain from sophisticated 3D simulations. What this does, though, is that it provides guidance as to where to look. Like you know now what the conditions are to get a good NUP process. You need high entropy, you need high proton to seed ratio, and so on. And so if you have a complicated 3D simulations with lots and lots of trajectories, this will tell you that, okay, you can probably just ignore these trajectories and instead only focus on these ones if you are interested in nucleosynthesis. And I think, yeah, that's all I have to say for today. So thank you. Thanks for having me.
Thank you, Amol, for a very nice talk. Do we have questions? Okay, I see a few hands already. The first one I see is Charles. Charles, go ahead, please.
So my question is, can any of this occur during neutron star mergers?
Probably not, because you need proton-rich conditions. you need an electron fraction greater than 0.5. So I would naively think that this is unlikely to happen during neutron star mergers.
But there are several regions and different components of ejecta during a neutron star.
Sure, fair enough. And yeah.
With
I
neutrino
guess some of them.
oscillations, who knows if mergers?
Yeah, fair enough. Yeah, some regions are more proton rich than others. Yeah, it would be interesting to see if you incorporate oscillations and such, if you can actually drive the electron fraction above 0.5. Yeah, good point.
And the next hand I see is Susan's.
Okay, great. I have two very quick questions. One, it concerns the supersonic or subsonic flow solution. So I guess my question is that when you showed us the improved yields in that context, then it seemed as if you needed to push to slightly heavier progenitor masses in order to realize subsonic conditions. And so even if you're successful in rescuing, I guess, the new P capture process from the suppression of triple alpha, I would think, because you have to rely on slightly heavier mediators, that your overall global production of the said elements might be slightly reduced. So to my mind, the two very different mechanisms you suggest to us, are quite different in that as you say, the neutrino evolution or neutrino mixing mechanism seems more universal. And so I guess I'm wondering what the lower cut on the progenitor mass in regards to resuscitating the new P process, what kind of impact it would have on what we would expect the element yields to be. So that's my first question. And my second question is, how do you make the fast flavor neutrino transformations? How do you arrange it to be close to the surface of the proto-neutron star? How does that control parametrically? So thank you.
Okay, thanks, Susan. So the answer to the first question, yes. Heavier progenitors are slightly more favored in terms of getting good new P process yields. And so if you integrate over the entire initial mass function, you will see that like most of the new P process production probably comes from the slightly higher mass end, but like you don't need to go too heavy, right? So these are 13 and we showed examples of 13 and 18 solar mass progenitors, but we even looked at 10 and 12 solar mass progenitors with subsonic outflows, and you do get a good amount of new P process there too. So I can't give an exact answer at this point as to what the cutoff in progenitor mass would be, because again, this would depend on actually doing this convolution with the initial mass function. Also, whether you get a subsonic outflow or a supersonic outflow isn't a function only of the progenitor mass. It also depends on the other boundary conditions like neutrino luminosities and so on. So here I showed an example where you get a supersonic outflow for a 9.5 solar mass progenitor. But if you had slightly lower neutrino luminosities, you could also get a subsonic outflow for a 9.5 solar mass progenitor. So it's more of a trend rather than like an exact separation that, okay, in this regime you get subsonic, in this regime you get supersonic. So you have to do the detailed calculation in order to know what the global picture is. So that I hope that answers
that's helpful.
A little bit the first.
Okay. Great.
And then and then for the second question.
Yeah.
Oh, sorry.
Go ahead.
Sorry. Then for the second question, in our case, we don't actually do a fast flavor oscillation calculation. We just, we cheat a little bit, right? We just say that, okay, at this radius, we'll just instantaneously mix all the flavors. We'll change the energy distribution. And so, as I said, that's only a proof of concept, right? So I mean, so complete flavor equilibration is like the maximum limit of what flavor oscillations can do in some sense. And so we just were looking at that simple picture. But then actually you can do a fast flavor oscillation calculation. And generically, I mean, there will be people in the audience who have done these calculations and who are experts on this much more than I am. But if you, maybe I can go back to the slide where I talk about this. Yeah. So basically, these fast flavor oscillations are triggered by non-trivial angular distributions of different flavors. So if you have differences between the angular distributions of nu-e and nu-e bar, say for example, one of them is more forward peak than the other, then you get these electron-lepton number crossings. And these crossings are what drive these fast flavor instabilities. And if you put the numbers in, you actually do get these oscillations within, like, say, a few kilometers from the protoneutron star surface. So you don't really have to, you don't really have to work that hard to get these oscillations to happen close to the neutron star surface. It just happens.
It's not special. It doesn't have to be arranged.
No,
it seems to just occur. Okay, that's very helpful. Thank you.
Mm-hmm. Yeah, you just need these lepton number crossings in the angular distributions. Like, that's the necessary and I guess also a sufficient condition to some
Thank
extent.
you.
Mm-hmm.
The next question I see is Kyle. Kyle, go ahead, please.
Hi, Amol. Thanks for the great talk. I had a couple questions. The first one, when you mentioned the slide where you chose where this fast flavor transformation took place, would that just be the radius at like MSW resonance?
It would not be the MSW resonance. Okay, I think we are on the correct slide here, right? So
yeah.
So you can see here. So these, if you look at the figure on the left, or the figure on the right, you can basically see the time or the radius at which these fast flavor instabilities grow, right?
Okay.
And I mean, so this is, I think these are the results of coherent calculation where you don't have collisional effects. And so this looks like very periodic in nature. But then if you do also have collisional effects on top of this, what you will see is that this oscillation probability eventually relaxes towards some asymptotic value, right? And then the radius that you pick in our prescription for like the complete flavor mixing is the radius at which that relaxation kind of becomes asymptotic. And so, I mean, these oscillations happen really quickly. You can see that already at, say, a quarter of a kilometer from the protoneutron star surface, you are already getting these large amplitude oscillations. But then, eventually probably they'll relax to some asymptotic value. And then, so we are essentially choosing the radius at which that happens. The MSW resonance will happen much further out. Like, that happens probably at a few thousands of kilometers or 10,000 kilometers from the protoneutron star surface. So by the time you get to that point, there is no nucleosynthesis. There isn't really anything that interesting happening from the NUP process point of view. So like the NUP process happens within a few 100 kilometers. And so that is like the regime of interest for fast oscillations and collective oscillations. And the MSW happens much further.
Okay, cool. That makes sense. And my second question, this enhanced NUP process caused by this flavor mixing, did you talk about how if that would add a significant amount more energy behind the shockwave at all, or like would it affect the shockwave at all beyond what neutrinos already expected to do?
So I mean, okay, so if you have flavor, fast flavor transformations happening, before like the actual core collapse supernova explosion. So let's say if you have a shock wave that is stalled somewhere because it has run out of energy, and then you have neutrinos streaming out from behind the shock wave. And let's say if you do fast flavor transformations in that regime, yes, you can increase the average energy of electron flavor neutrinos and antineutrinos, and then you can deposit more energy behind the shock wave. So that will affect the details of the supernova explosion. But the calculation that we are doing here assumes that the supernova explosion has already happened. And the hydrodynamic outflows that we are simulating are like the post-explosion neutrino-driven outflows. And so there, whatever neutrino mixing you do or whatever changes you make to the neutrino energies, they won't affect the explosion itself because that has already happened. But they can affect, like the amount of material that you drive out or how fast you drive it out, depending on, where exactly you do this mixing. If you do the mixing close enough, if you do the mixing basically right at the neutron star surface, within the heating zone, within the zone where the neutrino heating is effective, then it will also affect how you drive these neutrino-driven outflows.
Okay. And would you expect that to affect the supernova light curve or something? Like, is some observable for this happening?
Possibly, yeah, because the light curve would depend on what nucleosynthesis you get from this.
Okay.
Right. I mean, so yeah, it can. I think that it could have an effect on that. Yes.
Okay, cool. Thank you.
And we have one more question from George. The floor is yours.
Thanks, Amol. That was a great talk. Just
George.
a quick question on the NUI capture on neutrons. You mentioned that the sweetest scenario was one where you had, a higher energy for the NUIs. So they would more easily win the competition between NUI on neutron and NUI bar on proton. But my question is, and so that's wonderful to leverage that, because that's been our nemesis in trying to get the R process, of course, to work in neutrino heated outflow. But my question is this, one thing I've struggled with is that, of course, in that channel, NUI on neutron, you have the Q value in your favor, whereas NUI bar on proton, you do not. So I'm just wondering if you can lower the overall energy of both NUIs and NUI bars. What you will see is that disproportionately that NUI on neutron channel will win out over NUI bar on proton, just because of the threshold.
Right. Yeah.
And the energies of the neutrinos can still be fairly high compared to the threshold, but you'll see that effect. I'm just wondering if you thought about doing that, lowering the overall luminosity. I don't know whether, that's a function of opacities or the time at which this happens, but or the.
Right. So we didn't play around with the luminosities and average energies that much. Like, we just used a fixed value that we took from some simulation. But yeah, you're right. So we do see this effect, right? Let's say if you were to choose exactly equal luminosities for NUI and NUI bar, then like the fact that NUI capture on N does not have a threshold, right? That will drive the YE slightly more towards the proton rich side.
Sure.
Right. So, and then to make it slightly better for the NUPI process, we also used a little bit higher luminosities for NUI rather than NUI bar. So, instead of say YE of 0.52, you get YE of 0.58. But then I would imagine that you can also go the other way, right? If you want to instead get more neutron rich conditions, then yeah, you could certainly play this game where you try to, use the threshold, and then, yeah, I mean, you can change the relative luminosities of NUI and NUI bar. Yeah, and then you can maybe get YE of 0.48 or something, which gives you this alpha rich freeze out.
Then you're very good. And then you're also doing this in conditions where the entropy is actually significant.
Yes.
So, of order 100. And I'm just wondering, the energy scales are quite different, of course. So you're dealing with a temperature that's, typical thermal energies of particles are going to be a few hundred keV or maybe 500 keV. Nevertheless, the entropy may be high enough that you get electron-positron pairs. And then what I said about the threshold also applies in that positron capture on neutron. So I'm just wondering if you've looked at the contribution from that, or if it's just small compared to the neutrino capture channel.
Yeah, so I do know that contribution from electron and positron capture is built into the Skynet reaction network, but we have not tried to isolate those contributions, like how much comes from neutrino capture versus how much comes from electron positron capture.
Very good. Thank you.
Okay, I don't see any more questions. So let's all thank Amol again. And
Thank you.
thank you
Yeah, thanks
everyone
having me.
for great discussion. And we hope to see everyone in 2 weeks' time.
Thank you, Amal.
Thanks, man. Thanks, everyone.
Thank you.
Thank you.